we're going to start talking about charge and specifically the force of gravity. So the stuff I'm going over right now, a lot of it will sound familiar. You've done bits and pieces of this over the past couple of years, okay? So we're going to work from there. So first off, basics. Hopefully you remember this. Only electrons move. You can't move protons. You move protons, things go boom.
Doesn't the atom change like the element?
Yeah, it changes. You are basically you are an alchemist if you because you are changing what the matter is.
What were they trying to do? Make gold out of what?
So only electrons move, and we consider whether or not something is charged based on the number of electrons it has. Okay. All right. The amount of electrons above or below neutral. That's where we're at. Here's one way to look at it. If you have more electrons than protons, something has a negative charge. If there are fewer electrons than protons, it has a positive charge, and if they are the same, it is neutral. Now, throughout this entire deal, we're referring to net charge. Okay? I.e., like, you know, when you have an atom, you take, if it's balanced, you take all the positive charges, all the negative charges, you add that up and you get to 0, and it's neutral, right? So we're talking about things that are above or below neutral. And since the electron's the only thing that moves, that's what we're referring to. All right, moving on. Now, there's something that we refer to when we talk about basics of charge, and that is ground. Sometimes when things have more or less charge, you can do something called grounding. You guys, if you've ever changed a battery on a car, if you have a house with a lightning rod, that's what this is going. Basically, it's saying that the Earth is so big that it can both give up and take electrons. Like whatever we do to it, we're going to be okay. All right? So if you have an object that is positively charged, like this one's positively charged, that wants to be neutral. So if you put it in the ground with something, all right, that has an infinite number, or a seemingly infinite number of negative charges, that wire, path of least resistance, you're going to get charge moving from the Earth up to the sphere until it's balanced. Okay? You're not going to get more electrons. Like once it's balanced, they're going to stop moving. It'll be in equilibrium. But it's going to move that way. Same thing the other way. If you have something that has a negative charge and you put it into the Earth, the excess electrons will go down the wire and into the Earth until it is neutral. Okay?
So the Earth is kind of like the, what do you call it? Like, it has a whole bunch of electrons.
Most of us are neutral, right? If we did not, I want you to imagine how horrible it would be if we were not electrically neutral. What would happen with everything you touched?
The Earth, like,
Every time you touch, like if the Earth was underground and we had to like discharge other ways, holy cow! Everything you did you'd be either discharging or it would be discharging. Okay, I had one day, I don't know why, to this day I do not know why, but I swear everything I touched, even insulators, made like sparks. And I'm talking like I actually had like, you could see the blue light electricity arcing. I don't know, everything I did was touched it and it shocked me. It was horrible. But that would be kind of, was like, if we weren't electrically neutral, we'd be living like that. Okay. Let me see here. And so, before I go too far into that, I want to add this bit to it. All of this right here is based on the idea that charge is conserved. Okay? It's new. I really hope there was a sarcasm level on there. Okay. All right, charge is conserved. Is one of the things, the conservation. We have conservation of mass, conservation of energy, conservation of momentum, conservation of charge. Probably one or two others. All right. So basically, what that says is that you don't really make charge, but you can move charge around.
I
Yes.
have a question. Okay, so whenever you have like thunderstorms,
Uh-huh.
and there's like lightning and stuff, what's going on there? Like, is it
Um,
the same kind of concept?
So charge is conserved. Yeah, you can move charge around a system, but you can't really lose it. All right. This should be very familiar. Insulators and conductors. Insulators resist the flow of electrons. Now that is a key word in there. It is resist. Resistors do not stop. Insulators do not stop charge from moving at all. They just make it really, really hard for charge to move. Conductors make it easy. As an analogy, you guys, when you cook, most homes have wooden spoons in them, right? Because if you stir with it, it's not going to get hot. Now, if you're a bit of an nincompoop and you leave the wooden spoon sitting on a hot stove, it will eventually get hot. Okay, because it will heat up. There is still the flow. All right, the flow of energy, but it resists it. That's what it is. It doesn't stop it. It just resists it. Conductors allow the flow of electrons. They make it nice and easy. Materials conductors are metal, generally tend to be metal or things like that. Rubber and plastic tend to be good insulators. Here we go with charge by the numbers. All right, charge is a fundamental quantity. Okay. It is the smallest unit of something. You cannot have a partial quantity of charge. Okay? You can have 1 electron, you can have 2 electrons. You cannot have half an electron. All right? You cannot do this. Now, we measure charge using coulombs. Think of this like we measure mass using kilograms. Okay? Mass is a fundamental unit, so is charge. And now it also note the charge is positive or negative. It is positive or negative because, well, there's different types of charge. We are going to speak particularly about electrons, so everything we're going to be doing is going to have negative. All right, will be based off electrons, which electrons have a negative charge. Okay. Note that the negative goes with the coefficient. That is the part that is relating to the charge. This negative 19 over here, that negative only deals with the magnitude of the number itself, not the type of charge. Okay. Let's see. That has like a negative thing in our head, all right? But when we talk about charging, it gets a little bit messy with electrons lost and electrons gained. So first off, boom. So if something is positively charged, that means it has less electrons, a smaller number. All right, less electrons than protons. Okay? Now, if it has something that says you solve something and you end up with negative number of electrons, okay? So if you have negative number of something, that means you lose it, right? If you look at a bank balance and it says -5, that means you spent $5. So negative number of electrons, that means you lost them. But if you lost those electrons, that means that you are positively charged. Okay, see how that kind of works? It's kind of weird.
Yeah, Guillermo has a corny joke.
He does? What's his corny joke?
Remember that? It's 2 atoms, right? It's a dad joke.
It is a dad joke. All right. So the anecdote you guys gave me to help you guys remember this. Hey, I think I lost an electron. Are you sure? I'm positive. You lose an electron, you are positively charged. All right. So negatively charged means that you have a positive number of electrons. That means you are gaining it. If I have a positive number in my bank account, That means money I have. Okay? And that means that I am now charged negatively. If I gain electrons, then that means I have more negative charge. Okay. All right. Does that make sense? Okay. Honestly, you could also follow the words. The words tend to be good clues as well as what's going on. So even if your signs are getting you messed up, you can follow the words just like we do on anything else. All right, I'm going to move this page.
Wait, what is the C again? Charge?
No, the C is coulombs. Coulombs.
Like Coulomb's law?
Yes. Coulombs, as in how we measure charge.
Oh, like that number that you just showed us.
Right. Coulomb is how we measure charge. Okay. Consider it a relatively poor analogy. Consider it kind of like the number of charges is your number of atoms, and your amount of charge is when you start talking about what's the mass of those atoms. Okay? All right. Moving on. So let's do some practice. Do that part. Okay, ultimately, what we're talking about here is it's a conversion. Moving between electrons and charge is a conversion. So if we set this up, we want to know how many electrons are gained or lost if something has a charge of positive 4.6 microcoulombs. So first off, is it going to be gained or lost? Just based on the words, on what you see so far. What's the charge?
It's positive, so
If it's a positive charge, all right, it lost the electrons, right?
Also, if it was negative, it would have a
Right. Negative means that basically that's been added to the pile because it's already a negative pile.
Oh, okay.
If it's already a negative pile and you add more negative to it, it gets more negative. Okay. Yes. Okay, let's talk about the microcoulombs. Okay. If microcoulombs, anybody remember what that is?
Is it 9?
Nope, that's nano. Nope.
Oh, 8.
Nope. Most of our stuff is going to be in threes. Micro is times 10 to the negative 6th.
Oh.
Okay? So if you've got 4.6 times 10 to the negative 6 coulombs of charge, how many electrons does that translate to? We know that one electron, or one charge, is negative 1.602 times 10 to the negative 19th coulombs. That's how much one is. Right? Do a little bit of math in here. 4.6 e negative 6 divided by 1.602 e negative 19. We get 2.87. Negative 2.87 times 10 to the 13th electrons. All right. So if you have a negative negative number of electrons, what does that mean? They are lost. Well, yes, you're positive. Negative electrons, yes. Because what happened to the electron? He lost the electron. Okay, so negative electrons are lost. Okay? All right. We got this part? Any questions?
So that's like
Micro translates to 10 to the negative 6. Okay? 10 to the negative 6. If we had K translates to times 10 to the 3rd. All right? Milli translates to times 10 to the negative 3rd. So I just took the micro and I translated that into scientific notation. Like, what is the numerical value of it?
okay.
And these are the other ones you're gonna use?
Like I told you, in the start of the year, we use milli, centi, and kilo. If it comes down to anything else, we'll let you know. Anybody have their pink sheet?
Okay, so you just skip the step of dividing it by x into the negative 6.
No, she didn't.
Uh-uh.
I'm still. I'll get it later.
All right, flip the side. If you look on here, all right, on the part that has the constants and stuff, bottom left-hand side, it has that. So if it says, like micro times 10 to the negative 6, and you have something that says 4.6 microcoulombs, you take your 4.6, and you just plop that times 10 to the negative 6 on the side. Okay? All right, Danilo. So I think the problem that you've got is that there's multiple ways to handle conversions. We've kind of taught over the top of it. I know because you don't deal with the times 10 to the negatives over there either. Not when you're doing your conversions, right?
Yes, we, yeah.
You do? Thought he said taught.
What do you mean?
Okay. Okay. Well, that's not what I'm not in there. I'm talking about. I'm talking about metrics.
Oh, yeah. No.
Yeah. All right. And this train track version of it kind of means that so you don't necessarily need to mess with it too much. You can just say, does it go on the bottom or does it go on the top? All right. But you can't always do that. Sometimes you have these weird ones like, and who's going to memorize all these stinking things? So rather than go, how many coulombs are in a microcoulomb? How many microcoulombs in a coulomb? We just put the times 10 to the negative 6th on there. All right, so if you want to know how many, there are 100,000 microcoulombs in every coulomb. So in other words, just plop that little times 10 to that on there. You have the sheet. Okay, I would like for you guys to do this problem right here. All right. So let's see if we're all in the same place. If you've got 1.2, excuse me, wrong place. You got 1.2 times 10 to the 8th electron. That's the quantity of electrons that we have. Okay? And we know that every electron, every charge is has a value of negative 1.602 times 10 to the negative 19. Okay? Just as a quick magnitude of order check, 8 plus negative 19 means that my answer should be something times 10 to the negative 11. So if I don't get that, I know that I messed something up and I got to double check it. So I multiply those two together and I end up with 1.92. 1.92 times 10 to the negative 11 coulombs. But it gained those electrons, right? So if it gained the electrons, it is more negatively charged. So that's where you see that negative carry over there. Okay? This is coulombs. So this covers the basics of charge, what is charge and how do you measure charge. The next thing we're going to look at is going to be what happens when you get charged together. All right? What is the force between charges?